Um, Hello, everyone. Um, in this lecture, we will start hypothesis testing and confidence intervals for the mean, okay, for the average of the population. Okay, um, first we'll talk about the point estimation. Right? So the point estimation of a parameter of a statistical distribution is, well, it's a statistic. Remember, what's a statistic? A statistic is a function of the observations. Okay? So it's a statistic that produces a single numerical value as the estimate of the unknown parameter. Um, Recall we were using two important measures. One is the centrality, and we just use mu for the centrality. And the other one is the deviation around the center, which is sigma squared, the variance. So a point estimator for the for centrality measure for mu is x bar, and s square, which is the sample variance, is an estimator for the population variance sigma square. Okay. So again, X bar is a statistic, okay, is a statistic that produces a single numerical value as the estimate of the unknown parameter mu, and S square is a statistic which produces a value that you can use for whenever you want to use sigma square, okay, you can use the value of S square instead of sigma square, right? So why do we need this? As previously mentioned, there are parameters for the distributions, okay? So mu is a parameter. It generally shows the mean of a distribution, or in normal random variables. For normal random variables, we have mu and sigma, which are two parameters of normal random variable. Again, remember what a parameter is. If you know the parameter, you can calculate the probabilities, right? So if you know mu and sigma of a normal distribution, then you can calculate the probability associated with that particular normal distribution. Lambda is a parameter for the Poisson distribution, right? So, well, the thing is that in order to calculate the probabilities, you need parameters, okay? But in real life, we never know them. Okay, so, well, so what to do then? What we will do is we will just take a sample, and using that sample, we will estimate the parameters using these point estimators. Okay, so, um, okay, so again, the mu and sigma square, well, they have two meanings. The first thing is, okay, so let me just write here, mu and sigma square. So they are the parameters of the normal distribution. Okay, sorry. Um, the Let me just take the eraser from here. Okay, so it's the parameters for normal distribution, okay, for normal, and and they show respectively the mean, okay, and variance of any distribution, okay, variance of any distribution, right, any distribution, okay. So, um, so the normal distribution is so powerful that we just use the notation of their parameters, which are mu and sigma square, as the notation for the mean and variance of any distribution. Okay, so for example, for Poisson distribution, the expected value or the mean of the distribution is lambda. So we say that, well, mu of Poisson is equal to lambda. And the variance of Poisson distribution is again lambda. So we say the sigma square of Poisson, or the variance of Poisson, is equal to lambda. Or for binomial, the expected value is n times p. Remember, n is the number of the experiments, and P is the probability that you get a success. So mu is equal to n times P. So what does this mean? The expected value of the binomial, or the mu of the binomial, is equal to n times P. So in fact, n and P are the parameters of binomial distribution, and its expected value, or its mu, is equal to n times P. And its variance sigma square is equal to n times P times Q. And Q, recall, it's just 1 minus P, right? Okay, so for example, we can say that, well, lambda hat is the estimator of what? Estimator of lambda, right? You can show that, well, lambda hat, which is the average of, okay, average of the observations, that is equal to x bar, well, is a good estimator of lambda. Or p hat, so what is p? P is the probability of success in a binomial distribution. You can show that again, the average of xi's, which means you just sum the successes. Okay, so let xi show the successes in when you just count a sample and divide it by n, the total number of samples. So this is again equal to x bar. X bar is a good estimator for p hat, but, well, okay, what do we mean by good? So there are two important measures for an estimator to be good. First, it should be unbiased, okay? And the second thing is it should have minimum variance. So remember, we say that x bar, okay, x bar and sigma, no, not sigma square, okay, let me just erase this. So x bar, okay, x bar, well, and mu, and here let me just say s square and sigma square. So remember, these are the parameters of the population, okay? These are the parameters of the population. They are constant, okay? Remember, they are unknown, and they are constant from sample to sample, okay? And can be estimated. Okay. And of course they are unknown, constant, can be estimated, and they just refer to a population. Okay, they are the parameters of a population, right? For x bar and s square, well, they can be calculated. Okay, so they are known, in fact. They are not constant; they are just random variables, and they just refer to a sample. So, for example, the x bar. Let's talk about the height of students, okay, in a university. So, if you're talking about the whole university, then the average height is just mu. Okay, so this is the average height of the students in a university. If you're talking about the class, for example, for our statistics class, the average of the class is x bar, right? And we just use x bar as a point estimator of mu. And if you just calculate the s square of a class, then that's that's an estimator for the parameter of the population. Okay. So since x bar and s square, they're random variables, they should have an expected value. Remember, expected value of x bar, we just calculated it. It has a variance and it has a distribution. So by good, we mean that, well, the estimator should be unbiased. And what is the definition of unbiased? Being unbiased, well, the expected value of estimator should be equal to the parameter to be estimated, okay? So how do we show this? Well, for example, x bar, okay, x bar is a point estimator for mu, and its expected value is equal to mu. Okay, so what does this mean? This means that, well, x bar is an unbiased estimator of mu. Okay, and as expected value of s squared, that's equal to sigma square. What does it mean? It means that, well, the s squared is an unbiased estimator of sigma square. Okay, and the second thing is that, well, it should have a minimum variance. So its expected value should be equal to the value of the estimator, okay? And its variance should be equal to its variance should be as low as possible. Okay? So in fact, when you think of the estimators. So let's say I have an estimator here. Let me just show it by mu hat. So in general, we just use hat, okay, hat for point estimators, right? So mu hat means that, well, that's a point estimator for mu. So let's say this is mu hat 1, okay? Let's say this is mu hat 2. This is the second estimator. And let's say this is mu hat 3. See, so if so mu hat 1 is a random variable, and each of these points are values of a realization of this random variable. So you just pick a class, let's say. This is your first observation. This is your first mu1 hat, right? And this is your second mu1 hat, third mu1 hat, and so on and so forth. It turns out that what if you just take the average of these mu1 hats, its center is its expected value is just at this red dot, okay? Which means, well, the expected value of mu1, mu1 hat, sorry, that's equal to the parameter that you are trying to estimate, right? And it has some variance, okay? And we will see that this variance is, we will try to compare this variance with the others. So let's go to mu3 hat, right? So mu3 hat has the expected value of mu3 hat is, again, that's equal to mu itself, because as you see, if you just take the averages of these shoots, okay, these shoots, the average is just this red dot, okay? So it means that, well, the expected value of the this estimator is equal to mu. But if you just compare its variance, okay, mu3 hat, let's say, this is smaller than the variance of mu1 hat. Why? So if you just compare these two, okay, this one and this one, you can see that, well, the shoots are just more scattered around the center if you just compare with the third one. So these are just much more concentrated around the center. So hence, the variance of this estimator is smaller than the first one. If you just look at the second one, it turns out, well, the expected value of mu, let's say 3 hat, no more 2 hat, okay, 2 hat, well, it's not equal to mu itself. Why? Because if you just look at the center of these dots, the center is somewhere here, which is, well, it's far away from the red dot. So when you just see this is accurate, which means its expected value is equal to mu, but it's not precise. Well, this one is accurate and precise, and this one is precise, which means its variance is small, but it's not accurate. It's not shooting the right target. Okay. Well, this is very similar to the previous one. So as you see, this one is an estimator, just like mu1 had. This one is another estimator. So if you just compare them, it turns out that, well, the expected value of theta 1 hat is equal to theta, okay? And the expected value of theta 2 hat is also equal to theta. But the variance of theta 2 hat, right, it's greater than the variance of theta 1 hat. And if you just compare it with theta 3 hat, well, theta 3 hat, it's not unbiased because its expected value is somewhere here, okay? And its variance is smaller than theta 2 hat, but larger than theta 1 hat, okay? Well, okay, these were, so these are the point estimators of the parameters of a population. Okay, so, well, in the next video, we will continue with the hypothesis testing.